Okay, yeah, let's get started. So welcome everyone to our 20th Climate Intervention Virtual Symposium. Our first speaker is Anna Tippett from Imperial College. Anna is a PhD student in space and atmospheric physics, and she's supervised by Edward Grishbert, and she investigates the effects of aerosols on precipitation. So today she'll be talking about evaluating simulations of ship tracks. So Anna, the floor is yours.
Cool. Thank you for the introduction and thank you for inviting me to speak today. So yeah, I'm a final year PhD student at Imperial, and I'm just going to talk about a bit of the work that I've been doing throughout my PhD. So with Ed and then also Paul Field at the Met Office. So this work, we've been simulating sort of aerosol cloud interactions inside ship tracks, which are this sort of really good natural analog for marine cloud brightening experiments. And we're going to talk about sort of evaluating or how to evaluate sort of model performance by using satellite observations. So a bit of background on ship tracks for anyone who isn't completely familiar. So they're these sort of bright linear cloud formations that form in the wake of ships. So we have our ships sail through and they burn fuel and they release aerosols that get carried by updrafts into the clouds above them. And these aerosols act as cloud condensation nuclei, so they provide more sites for cloud droplets to form. So on very short timescales, if we assume that the amount of water is held constant in the cloud, this results in more smaller cloud droplets and more reflective clouds, which is why we can see these very bright lines. And it's sort of led to this idea that instead of doing this inadvertently by burning ship fuel, if you did it intentionally, you could reflect more incoming solar radiation, and that would sort of cause a cooling effect and offset some of the warming we have due to sort of greenhouse gases. So this is known as marine cloud brightening, and is one of these sort of three big solar radiation management strategies that I'm sure we've all heard a lot about. So the idea would be to spray sea salt aerosol rather than sulfates, which are sort of bad for human health, and artificially brighten sort of marine clouds. So these it'd be relatively low level clouds and quite regional effects that would happen. So the marine clouds have sort of been suggested because marine stratocumulus regions are thought to be the most susceptible regions to aerosol. So here we've got this sort of albedo, so reflectivity, compared to the sort of log of the aerosol optical depth. So essentially a measure of this brightening due to the Toomey effects of this reduction in cloud droplet size. And we can pull out these five regions, which are the stratocumulus regions off the western coast of continents, which show where this effect is the strongest, so where you'd have the largest brightening potential. So this is sort of the region that I will be studying in this work, which is sort of off the coast of California, because it has this really, really high sensitivity to aerosol. So this all sounds great. Does my PhD exist? Why am I bothering to simulate MCB and ship tracks? Because unfortunately, it's not as simple as that. So the first order effect of this sort of brightening because of a decrease in droplet size and increase in cloud droplet number concentration happens on very short timescales, but isn't the only effect. So clouds can change after that sort of near instantaneous increase in cloud condensation nuclei. So you get this modification to cloud properties as an effect of the change in droplet number concentration. And these are known as adjustments. And these occur over much longer timescales and are relatively uncertain. So it's an important uncertainty just within the sort of field of cloud physics as a whole, but especially relevant to when you're considering MCB, because you want to cause this brightening in clouds, but what happens afterwards is still of sort of great importance. So the sort of crude splitting of these adjustments is into these two. So we have, if you have smaller cloud droplets, they can take longer to form rain droplets. So this is what this sort of drizzle suppression effect is. So take longer to form rain droplets, you suppress your drizzle, and the cloud has an increase in liquid water path, so holds more liquid water, and it exists for longer. And this means there can be more reflection of sunlight, so a cooling effect. Oh, a cooling effect. On the other hand, you can have smaller droplets, sort of increasing the efficiency of the entrainment of dry air from above the cloud top into the cloud. And this can cause the cloud to dissipate. So it can disappear, so obviously hold less liquid water then, and constitute a warming effect because it's not being able to reflect as much of the incoming sunlight. So these, as I mentioned, are quite uncertain, these adjustments. And it's really important to understand which of these processes happens, when, and why, in order to have confidence as an MCB as a climate intervention strategy. Uh, so this leads to the motivation of this study, which is to model these aerosol cloud interactions in ship tracks and essentially look at how good a model is at representing it. Because when we're considering like SRM strategies, we can use ship tracks as a natural analog, but we're not going to be doing it with sulfates and it's not going to be in the exact same way that ship tracks occur. So we want to be able to simulate exactly what we think might happen. So models are going to be a really, really key tool in sort of in further investigations into this. But sort of we need to take a step back and sort of think, how do we know our models are telling us the right thing? So this piece of work is more about trying to model ship tracks and evaluate how good a model would be at simulating marine cloud brightening and where it sort of is failing. So we're going to simulate some ship tracks and we're then going to compare them to observations of the same ship tracks and see where the model is doing well and where it's doing less. So as I mentioned, these adjustments occur over longer timescales. So we need a way to investigate sort of the time evolution of the aerosol cloud interactions. And in a model, this is really easy. We just get continuous model output, so we can really look at how the cloud is evolving sort of temporally. But in observations, this is a lot harder because a lot of our cloud observations are coming from polar orbiting satellites. So we get a single snapshot of a ship track like this, maybe like twice a day. And we want to sort of infer some time evolution from that. And the great thing about ship tracks is they have this sort of distance axis. So, I mean, the ship is currently up here, which is known as the head of the ship track, and points further along experienced the aerosol perturbation longer ago. So we pick our ship track and then we have this sort of distance along ship track axis, which we can transform into a time since aerosol emission axis. So we call it the time along the track. So a point down here might have experienced an aerosol perturbation 20 hours ago, and so we can infer how the cloud response varies over time. And this is going to be really important for doing a comparison so we can still get this information about the time evolution. So when I talk about evaluating our model, we wanted to sort of set out quite a systematic way to do this. And the main aim, I guess, of simulating ship tracks or simulating MCB is you want to sort of capture the correct shortwave effect. You want to capture the correct warming, cooling, whatever you're getting. But you want to get it right for the right reasons, and you want to be representing the processes within it accurately. So the first condition that we wanted to set was that we wanted the correct inside track droplet number, concentration, and liquid water path, so that we're sort of capturing what the actual values are, which are going to sort of impact the shortwave radiative effect. But we also want to get the correct time evolution of response, and this is going to be really key in investigating whether or not we're capturing the processes correctly. So we don't want ship tracks that just exist for days and days and days and never fade away because they're going to really sort of overestimate the like integrated shortwave effects. And we also want to see some sensitivity to initial conditions. So what like we've got this precipitation suppression mechanism and this enhanced entrainment mechanism, and we see that they are stronger in different conditions. So obviously you're not going to expect precipitation suppression when it's not raining. So we want to sort of have a model that represents this and represents the sensitivity to the initial conditions. You don't just want the same blanket response all the time. So now that we've laid out all of that, we can actually talk about what we simulated. So we picked this case of ship tracks off the coast of California in 2018. And there are lots of very bright ship tracks here, but due to just the modeling constraints, we only select these five to simulate because they're the easiest to make sort of do the observation analysis on and are quite representative of the domain. They're all large container ships, so hence why they all form sort of very large ship tracks. And then a bit about our model. So I'm using the Met Office Unified model, and I have a 1.5 kilometer nested simulation, nested domain that's driven by the global model. So we use Cassini two-moment microphysics coupled to a UKCA aerosol scheme. So we can really try and we can represent these aerosol cloud interactions and investigate sort of uh, how they do compared to the satellite observations. Um, so we generate our simulations and we generate our ship tracks, and they're in the right place because we're using real ship emissions. So we've really like used the exact same ships that we saw in the observations. So we see that they happen in the right place. They look sort of, if you just look at it quickly, they look quite good. But we see, I mean, the main difference here is we see that we have the model is missing these really sort of high droplet number concentration sort of regions and then in the domain. And this is due to the way we initialize our aerosol and the boundary conditions. Because we just don't have any aerosol sources over land. So that explains that. It's going to make our analysis a bit more complicated, but it's not a sort of physical process representation issue. It's just a sort of we're missing a source. So, like I mentioned earlier, we want to take all our ship tracks and sort of straighten them out and use the distance along the ship track axis as a time axis. So this is an average of all our ship tracks. Looking at in this column, the MODIS observations, and in this column, the model simulated ship tracks. And we're looking at droplet number and liquid water path. And we see that we have our sort of typical thing you see in ship tracks, that we've got a large increase in droplet number concentration where the ship is. And it's nice in the model that we see that it's not too wide because we're using 1.5 kilometer resolution. So our ship tracks start 1.5 kilometers wide, and it's nice to see that that isn't too big compared to the observations. Um, so if we just take an average of this sort of inside track region and look at the droplet number and liquid water path, we see that there's like a really nice match. So this first condition that I mentioned, where we're looking for the correct inside track droplet number and liquid water path, we see that they match very well. So where the aerosol is matches very well to what we see in the observations. But as we can kind of see already, our backgrounds are quite different. So even though where the aerosol is correct, it might not actually be that representative compared to the background. So we want to consider how large this change is inside the ship track compared to the sort of unpolluted background clouds around it. So to do this, we consider the sort of percentage enhancement of the sort of inside track region compared to the outside track region. And when we do that, we see very large differences between the model. So we basically see that our model so our model has this really long-lived droplet number perturbation. So it's not depleting at all over time. In the observations, it's basically returned back to zero by 15 hours, whereas in the model, it's sort of we've still got that ship track lasting for way too long. And then when we look at the liquid water path, we see that we actually have the complete wrong sign of the response. So in observations, on average, across all 5 of our ship tracks, we see the liquid water path sort of decreases and then returns back to normal or the same as the background after about 10 hours. Whereas in the model, it's just liquid water path increases the whole time. So this sort of this correct time evolution that we were looking for is not satisfied at all. Like we're not representing the process as well inside these ship tracks. So the question is why? Um, so we split our tracks into 2 different cases, trying to see if some cases are better than others. And the sort of best way to separate them is by the direction of travel. Because we see that basically we have 2 ships traveling towards the coast and 3 away from the coast. And the 2 ships traveling towards the coast, mainly traveling through precipitating clouds, so mainly their ship tracks are going to mainly be sort of clouds that were precipitating and then had the aerosol put into it. Whereas the other 3 don't really travel through precipitating clouds until near the end of the simulation. So we use this as a proxy for sort of splitting our ships into precipitating and non-precipitating cases. And when we look at our percentage enhancements for this, we see that For the non-precipitating ships, it's the model and the observations are much more closely matched. The time, so in the first few hours, there's quite a nice overlap, whereas at longer timescales, they start to diverge. So there's timescales of the processes involved are still not perfect, but we're at least getting the right magnitudes and the right signs. But in the precipitating cases, this is where the big issues really come in. So we see that the droplet number is really overdone, as well as the liquid water path, like the magnitudes are completely wrong. And this is where the difference in sign of the liquid water path responses come in. So in the observations of these ship tracks, we actually aren't seeing a massive liquid water path increase. So the precipitation suppression mechanism isn't really at play there. Whereas in the model, we're seeing massive liquid water path increases. So we're basically seeing that the model is too readily suppressing drizzle. And if we look at the precipitation in these sort of, so the non-precipitating tracks on the top row, the precipitating tracks are on the bottom row, and we have our control simulation where there are no ship tracks, and then the ships simulation where the ships are all turned on, and then a difference. And we just see a complete shut off of precipitation when we go from the control to the ships in the precipitating cases. So we looked into this even further to think like, is this realistic? Maybe our observations are wrong. Maybe the model is perfect and it's actually observations where all the problems lie. So we sort of take a step back and look at the whole domain and just where what the probability of precipitation in a pixel is based on the liquid water path and the droplet number concentration of that pixel. And we do it for all the model time steps of our simulation. And then we do it for the same domain, but over sort of 5 years of CloudSat MODIS co-located observations. So these are from 2007 to 2011, I believe. We basically just see the probability of precipitation in this sort of liquid water path droplet number concentration space is really binary in the model. So if you pick any pixel and look at the droplet number concentration and the liquid water path and is it raining or not, it's basically either yes or no. There's not much nuance to it. And this will come in from the way that the model and the way the model parameterizations are representing this sort of production of precipitation. And then so when we take our background sort of pixels on average and then the ship track pixels on average, they basically get shifted just across this very sharp boundary in probability of precipitation. And this means that precipitation is completely shut off. So it's kind of unrealistic, but also, I mean, this case of ship tracks that we've sort of chosen to simulate just happens to be very fortuitous that it's right on this boundary. Like if we happen to be in a much more polluted case, then there probably wouldn't even be any precipitation in the first place to shut off. Or if we were even cleaner, we would still be on this side of the boundary, so we wouldn't have the complete shut off. But essentially, it's quite a nice way to evaluate how a model is representing precipitation, and how unrealistic that is by comparing. So, like, we would expect a much more nuanced spread of precipitation within the domain. So, I guess the key thing to highlight here and what we found throughout the study is that you can simulate ship tracks to an extent, but for the purposes of MCB, especially, you're going to want to be able to do them in precipitating cases. Models have a bit of ways to go to sort of accurately simulate them. And current model parameterizations aren't completely suited for this really sort of high aerosol concentration perturbation. So further work is sort of needed looking into that. So yes, just to summarize, the model can reproduce the droplet number and liquid water path values inside ship tracks. So if you look at just where the aerosol that we've put in is, so there's this correct inside track droplet number and liquid water path condition is satisfied. We see large differences when we look at enhancements from a background. So the representation of a background is really important when doing these case studies. And this time evolution is not correctly satisfied, or not, yeah, not correct in the model representation. And this comes in from precipitating cases where the model too readily suppresses rain and has this very binary view of whether a pixel can precipitate or not. So this sensitivity to initial conditions is almost satisfied, but not correctly. Like if you only ever look at non-precipitating cases, this current model setup would be quite good at simulating ship tracks, but these aren't really the cases of interest. So more work is needed to work on the precipitation side of it. And yeah, I didn't really mention this, but the current model setup would really overdo a cooling effect because this lifetime effect from precipitation suppression is too represented too strongly. So if you just didn't look at observations, just modeled ship tracks or MCB using this current setup, you'd look like you'd get a lot more cooling than you actually would. So it's important to address if models are going to be used for simulating MCB. And then this sort of framework, I guess, is also a model independent, like it doesn't need to necessarily be applied to this model. So it'd be a good way to evaluate how good a model is at representing these processes. And we have a preprint out, which is the QR code for it is there. And yeah, I'm happy to take any questions now. But thank you.
Thank you very much, Anna. That was great. We've got one hand up from Andrew Lockley and two claps.
Hi, yeah, the effect you're describing where you are collapsing to a binary, it sounds like a similar mathematical phenomenon where you in AI, when you've got a linear function and you try to collapse it deliberately to a binary with a squishification function. So if you just run an inverse squishification function on your data, you might find that you can restore the linearity of the drizzle production without doing too much heavy lifting. It's just one equation that you need to insert, and you might find that by manually fiddling with the parameters of that, you get it to basically turn the data back to what you want. So just an idea. I don't know whether it will work, but it's at least worth looking at. It's a simple fix if it works.
Yeah, I might send you a message afterwards. But yeah, because we've only found these results relatively recently, and we've got some updates to the model version, so I've got to check it's still an issue. But I assume it will be because I don't think they've changed anything in the parameterization. But yeah, be good to fix.
Yeah, keep an eye on the chat. I'll send you a link.
Cool. Thank you very much.
Thank you, Andrew. Any other questions? I guess I was just wondering if this is just like a quirk of Cassini as it is now, and if you like twerk the parameterizations, maybe you can like in this graph that you're showing here, like get something that's closer to Passat modus, just like tweak some parameters.
Yeah, I guess it's a quirk in Cassini in the sense that it's a quirk of the parameterizations, but it's not relevant just to Cassini because the auto conversion parameterization, which is the production of rain droplets from cloud droplets, we're using K and K, so that will be relevant in many different cloud microphysics schemes. Like many will use that same parameterization. But yeah, I guess it's just to highlight something that's good to look at. But yeah, the aims are to tweak with the parameterization and see if we can do anything to change this representation and modify it more so it's more suited for these conditions. But yeah, question.
Okay, thanks. Any other questions? If not, we can move on to Ali, but please feel free to use the chat if you want to ask Anna some further questions. Thanks again, Anna. And Ali, do you want to share your screen? And so our next speaker is Ali Akherati from the funding agency called Reflective. Ali is a data scientist at Reflective and will be talking to us about Reflective's emulator for stratospheric aerosol injection. So Ali, the floor is yours.
Thanks, Matt. Yeah, thank you for introduction and thanks for the time and inviting me to give a presentation. I'm a data scientist. I have a background in aerosol microphysics. I did my PhD back in Colorado State University. I've been working with Reflective for 5 months now, and I want to acknowledge all the colleagues that they have been working on it for almost a year and a half now. And it's the work of many people, collaborators at Cornell and UC San Diego as well. And I'm going to talk about the web-based emulator that we have built for a stratospheric aerosol injection, the overview and the latest update. I don't think I need to give a motivation why we need to do research for climate geoengineering in general, but just as an overview, this is a graphics from Ricci et al. 2025 showing that the tipping point for different elements the probability of tipping points are gonna increase as the temperature goes up. What I would like to focus is like, why do we need an emulator for especially a stratospheric aerosol injection? We need simplicity for educating public, just accessibility and also accuracy of the data. As we know, running climate models are expensive. They take about a week to few months, depends on what kind of complexity we want to have in the model and like how many years we want to model, etc. And in order to make this stuff available into the public, we need to have, more simpler version that people can iterate through and, educate for policymakers or for general public, and make it accessible people who don't have climate science background. So this is the screenshot of what we have built at Reflective, and I'm gonna walk you through as a live demo at the end of the presentation, but you can select your scenario, you can change the visualization, and we show the map on the left side and the time series for a given impact or variable you choose. There are different impacts that we have. Some of them are temperature based, some of them are precipitation based. We recently added Arctic sea ice extent as well, and we have these socioeconomic pathways that are based on the emissions in the future, and you can select 8 different ones. I'm gonna show you at the end. What's happening in action, and I'm gonna use simulator and emulator interchangeably, but this is basically underlying emulator that we try to statistically represent the data. So we select the emission. Currently, you choose the emission based on the socioeconomic pathway. So as I've shown you, there's 8 different of those. Then we run finite amplitude impulse response. Let me just move response simple climate model, which is called FAIR, to determine the global average temperature for a given year. And then you choose the impact of interest or variable of the interest. It can be precipitation, temperature, ice fraction, etc. Goes to the emulator number 1, and then it calculates the spatial distribution for a given variable for each year. And then you can create the map for a version where there is no SAI, and create the time series and the distribution of the values for a given year or given decade. And then you can choose your SAI cooling target temperature, let's say 0.5 degrees C above pre-industrial or 1.5 degrees C. And the range right now on the website is 0.5 to 2.5 degrees C. And you can choose also deployment start year. And you can take the values from the annual spatial distribution from the emulator number 1, it goes to emulator number 2, and then you calculate the spatial distribution for a given value for a selected SAI scenario. Basically, it gives you the delta if you deploy an SAI scenario, how much, let's say in the temperature variable, how much cooling you get. So for each grid cell, you get the delta, and then based on the map you have previously made, you can create the map for the SAI scenario with the time series. Some of the specification that we have been using is we are using the ESM we are using is vacuum CSM2 for the data. We use Gauss with 3D ensemble model for a multiple degree of cooling. This is described in Visioni et al. 2023. The SAI period that we are running is 2035 to 2070. And the natural variability, the way we calculate is we detrend the simulated values, and then we look at the variability within ensemble members and calculate the standard deviation. So I'm going to walk you through how each emulator is working. So in this scenario, we select, you have the emission scenario. We run SSP to 4.5, which is the balance scenario. Again, run fair to get the global mean temperature value. You can imagine, you get the values from 2025, for example, all the way to 2100. So it gives you the global mean temperature for individual years. It goes, and then we have the simulation runs from air system model, in this case, vacuum CSM2. And for each variable, we have the values by latitude and longitude. So for each year, we have the values for each grid cell, and we have the global mean temperature anomaly from FAIR. Then you can build an emulator based on this data. Let's say, in this case, we are looking at the surface temperature. You have the temperature anomaly on the x-axis, and you have this is like one grid cell that I'm showing as an example, and you can fit the values to that. So for a given temperature anomaly, you can calculate what would be the temperature for individual grid cells. So that's how the emulator number 1 works. Emulator number 2, we have 3 different SAI scenarios with different cooling target, 1.5 degrees C, 1 degree C, and 0.5 degrees C cooling target. And we have the no SAI scenario. So again, for each one of those, we have 3 ensemble members. We get the average global temperature anomaly, the difference between the SAI scenario and no SAI scenario. And for individual grid cell, you have, for a given variable, you can calculate what the SAI minus no SAI would be. And then in this case, given that we have 3 scenarios and the average ensemble member, you get 3 points based on the average global temperature anomaly on the x-axis, the difference between SAI minus no SAI. For each grid cell, you have the difference as well, and you can get the fit value. So that way, when you choose the cooling target, you can calculate what the difference would be for given grid cell for a given variable, and then calculate the difference. Again, just stepping back, how everything works, you get the annual distribution. The spatial distribution from the map goes to the emulator number 2 based on the SAI scenario. You calculate the difference, and then that's how you get the no SAI map versus SAI map. We recently added custom injection to the simulator. This is based on Cider. I believe this is the pronunciation if I'm not butchering it. It's a climate intervention dynamic emulator done by Jared Fairley et al. In Cornell in 2025. The preprint is out. So essentially what it does is just you specify the amount of SO2 in a given latitude. It calculates the AOD, and then it gives you the temperature response globally, how the temperature would change. So we plug this emulator on top of what we have. So as you have the temperature, then you can go through the previous workflow I shown you and then calculate the SAI versus no SAI for a given variable or impact. I also recently worked on the Arctic sea ice extent. I don't want to go spend too much time and go to the details. Happy to answer any questions afterwards, but the nature of the sea ice extent is a little different. It's not the linear fit. It's a logistic function, given that it goes from 0 to 1 all the time, and then it's not exactly linear. So this is like showing you the final results of, on the validation side for 10 years period. This is from CESM on the left side. This is the emulated value, and you can see the difference. It's satisfying given that it's it's a very complex system to build statistically, and it shows the difference between 0 to 0.1 plus minus. So in terms of limitations, we are not doing any interruption or termination. We don't show those given that we only include the 10 years average. The emulator has been developed only by a limited set of model runs, as I mentioned in the specification slide. The impacts that we have been showing, and climate impacts we have been showing, are also limited. These are, robustly driven from temperature and precipitation based on the literature. And also, the simulator is only based on a single model, which is CSM WACM 2. So for the future work, we are trying to incorporate more data and more models to broaden the scenario that can be simulated and better represent the uncertainty. We are working to also include spatial and temporal downscaling to build a better to expand the set of climate and socioeconomic impacts. Also adding more impacts to the simulator. Those are already analyzed based in the SAI literature, such as air quality, sea level rise, and other variables as well. And developing a benchmark framework in order to validate the simulator's performance, which is not specifically simulator performance, but the underlying models that we use to build a simulator. With that, I would like to show you the simulator. So this is, if you go to simulator.reflective.org, actually, if you show it to somebody, they can go through the tutorial and just get a sense of, if they don't know anything about climate geoengineering or SAI in general, they can go and explore. But here is the panel that I was showing the screenshot of. You can build your scenario, so you can choose the different socioeconomic pathways. Let's say this is like a high fossil fuel use. You can change the cooling target to between, again, 0.5 all the way to 2.5 degrees C. So let's say it's 1.5, and you can change the deployment here from 2035 to 2090. And these are like pop-ups that you can hover over and just read the information. You can customize the visualization, depends on which impact you're using. We have the max mean temperature, extreme heat exposure, and freezing exposure. There's water availability, heavy rain exposure, and rain exposure as well. Then you can change the decade that you want to look at. As you can see, there's a shaded area on the right side on the time series, and you can move along and change that, and the map is going to respond. So what we show on the left side is the 10-year average values over the map, and the time series showing from 1850 all the way to 2100, and depends on which year you are choosing to deploy for SAI. The blue line moves, and there you go. And there are some statistics in terms of, how much SO2 in a given year. That depends on which decade you're using, how much is gonna be needed based on the cooling target. There's, relative to Mount Pinatubo, there are some statistics of the number of planes and the direct cost of deployment. And these are all based on the literature. The other one that I want to show is the custom injection. If you don't see the custom injection on the here, you just need to go to the setting and you can turn it on. It's going to show up here. And when you click on it, toggle to turn on, you can go to the edit. So now you have 7 different latitudes for deployments. There are some default values that you can choose, default scenarios you can choose. But I'm gonna go here, just make a custom one. Just gonna copy this. And then when I hit save, it's gonna start do the calculation on the back end, and you can see it's loading, and then it gives you the value. So I'm gonna change it to end of the century, 2090 to 2100, and you can see the difference between SAI and no SAI. You can choose for custom injection, we have water availability and the temperature. And the new version, which is still on development, we also have the sea ice extent as well. So you can choose between temperature, water availability, and sea ice extent. So this is the sea ice extent. You can see how between the SAI and no SAI scenario, it has what the differences are. I think I went a little too fast. I was planning to go for 20 minutes, but with that, happy. If you have any questions or comments or anything, please reach out, info@reflective.org. My email is ali@reflective.org. If you want to go to the simulator, this is the URL. Thanks for your attention. Happy to answer any questions that you have.
Thank you so much, Ali. That was great. That's a really exciting simulator. Does anyone have questions? Oh, Mike, go ahead.
Do you do anything with respect to AMOC and what would happen if the Atlantic Meridional Ocean circulation collapses?
I am not familiar with AMOC, to be honest, and I believe these are all the scenario, this is so that might be probably a special case that you need to run the CSM model for, and I believe those are not included in the training data set. So the answer is no. But I don't know, Dan, do you want to add any comments, or I don't know if he's on the call.
Yes, I am. I was actually just writing on the chat. We don't, as in it's sort of the response is already embedded in the simulations that we have. However, when it comes to the single point injections, we do have a paper that I was posting that we published recently about how EMO could respond to different injection location and scenarios. So essentially, one of the plans probably with CIDR is to add another EOF that would respond dynamically to AMOC in future versions of the emulators.
Cool, that sounds great. Any other questions? If not, we can just stop here. And if you have any other questions, please feel free to email Reflective or ali@reflective.org. And with that, I'd like to thank both of our speakers today and hope you can join us next time. So thank you very much.
Thank you.
Bye, guys.